Welcome everyone to a new episode. Today I'm talking to Francesco Paesani regarding how to simulate a phase diagram for water. He's developed a new algorithm for this, and we're going to be focused on the theoretical fundamentals of that model, but also how to implement it in practice. I hope you enjoyed the discussion. In terms of the paper, we have it on the screen. It's called Realistic Phase Diagram of Water from First Principles Data-Driven Quantum Simulations. I think to give background to the topic we're going to be discussing, it would be useful, I think, to introduce the concept of modeling water and the phase diagrams of water and what the challenges are associated with that. Would you mind just giving a few minutes introduction to the topic and why it's difficult to model water in particular?
Of course. So, water as we know it is usually called the life's matrix because life as we know it only occurs in an aqueous environment. That doesn't mean that couldn't be another type of lives in a different environment, but the one that we know and is on this planet cannot exist without water. Somewhat unique to water. In particular, water can form these hydrogen bonds that are peculiar and are characteristic to determine all possible solvation processes around us, are important to transfer protons in a biological system or in a material system, so that protons are part of this energy transduction that happens in nature. And so electrons go in one way, protons go in the other way. And that is only possible because the strength and the topology of these hydrogen bonds that water can form is very peculiar. Only water can do that. And so because of this interplay between energetics and structural properties, water has been first and foremost the liquid or the substance that people have studied the most. Because as soon as computer came online, the first thing that people tried to do was to model water and liquid water in order to understand at the molecular level how nature works. And so the first simulations of water actually was in 1969, and there was a Monte Carlo simulation, and the first molecular dynamics simulation was in 1971. So it's almost 50 years that the researcher and the scientific community has tried to come up with a molecular model of water that is able to reproduce the properties from the gas phase clusters to liquid water to ice and water in contact with different materials, different biological systems, and in different thermodynamic conditions. And the challenge is really like this transient or fluctuating hydrogen bond network that is very collective, but also relies on very local structures. And because of this, the strength of these hydrogen bonds change as a function of temperature and pressure, depending on the environment, it is very difficult to develop a molecular model that is able to be completely transferable across different phases and across different thermodynamic states.
Mm-hmm. If I can interrupt there for a little bit, when we talk about these hydrogen bonds and how they fit into the larger picture and also how they vary with different parameters, could we stay on that topic for a little bit? Maybe sure. If we particularly focus on how the hydrogen bonds and their characteristics depend on external factors like temperature. What are the factors that it depends on, and in what way do the hydrogen bonds depend on those factors?
Yes, so every water molecule can form on average 4 hydrogen bonds, because a water molecule has 2 hydrogens, and so can donate 2 hydrogen bonds through these 2 hydrogens. And then the oxygen atoms have 2 long pairs, so are 2 pairs of electrons that can be engaged in accepting hydrogen bonds from neighboring water molecules. Mm-hmm. And so, since in a liquid the water molecules can move, can rotate, can translate, the amount of energy that is given to the liquid depends on average, or in simple terms, to the temperature of the system. The higher the temperature, the more mobile are the water molecules, which means that the hydrogen bonds are becoming a little bit less, are more prone to be broken and to reform. So the dynamics of the hydrogen bonds becomes faster. And as you go toward the boiling point, then the kinetic energy or the temperature is enough for the water molecule to actually break the hydrogen bond and actually escape from the liquid. And so you go into the boiling of water. On the other hand, when you lower the temperature, the water molecules, the motions of the water molecules become extremely slow, and each water molecules try to optimize the strength and the geometry of these hydrogen bonds. And then you go toward freezing of water, and so you are going to form ice where the water molecules are stuck in well-defined crystallographic positions, and the hydrogen bonds are at their maximum strength because they are oriented in the perfect way to minimize essentially the free energy landscape, which is related to this energy of these configurations.
Mm-hmm. Okay, if we also focus on the second point, namely how these hydrogen bonds are connected to the wider system, you said that there was a very local aspect to how these hydrogen bonds work, but that there's also a networking effect, let's say, or that there's a macroscopic element to this where they're all connected. Would you mind painting a picture of how that varies compared to other materials in particular? So if we take something more conventional like some solid or whatever, like you would also have local connections, and you would have, at least a connection to electrons or whatever it might be on the other side of this material. But if it's not necessarily the same, what are the differences from more conventional materials and putting that into a context of water?
Yeah, so since each water molecule tend to form this 4 hydrogen bond, but especially in a liquid, everything is moving. So when a hydrogen bond breaks, then is the collective motion of the surrounding environment that has to rearrange in such a way that the water molecule that has lost one hydrogen bond can find another partner to make another hydrogen bond. So sometimes people depict that like a defect that is propagating, because you break an hydrogen bond, one water molecule suddenly feel under-coordinated and is going to look for another partner. But the other partner needs to also be under-coordinated, and so it must be a collective, a cooperative effect, where one water molecule breaks an hydrogen bond, another water molecule at the same time has the possibility to donate the hydrogen bond. And so it is a very local effect, the formation of the hydrogen bond, but it depends on the fluctuations of what we call the hydrogen bond network, which is this extended network of hydrogen bonds that propagates across the entire liquid.
Mm-hmm. Okay. As a follow-up question to that, would it be fair to say that the characteristics of water changes also within the different phases? So naturally there are key distinctions, right, between the solid phase, let's say, and the liquid phase or the gas phase of water. But within one of these phases, let's say you have boiling water, I would presume, and maybe this is me being too naive, but if you have, let's say, water that's boiling rapidly, not only do you have molecules that are escaping these hydrogen bonds and then escaping the liquid altogether, but could you also have effects on the wider network in terms of there having to be a higher frequency of molecules being paired up? And does that sort of affect the characteristics of water in any way? Or is it fair to say that within the different phases of water that you have, the behavior is kind of agnostic to the temperature or the pressure within, so long as it's in that phase?
So we can distinguish two different types of regimes. So the solid phases, and then what are called the fluid phases, which are liquid and gas and vapor. So within a liquid, the hydrogen bonds are going to be uniformly distributed given a well-defined temperature and pressure. And so if you look at a glass of water at a given temperature and a given pressure, all the hydrogen bonds will look the same across the entire liquid. And the same is true in the gas. Obviously, in the gas is going to be very unlikely to have an extended hydrogen bond network because the temperature is much higher, and so is the thermal energy that is provided through the heat breaks all possible hydrogen bonds. And so in the atmosphere, maybe we can find dimers of water molecules, maybe small clusters, but we definitely cannot find the large hydrogen bonded connected systems unless not under equilibrium situation. So it may happen that some small droplets form of water that are hydrogen bonded connected, but usually there may be some other species inside the droplet that act as a nucleator. A pure water droplet in the atmosphere is going to be very unstable, and so it will evaporate depending on the temperature of the system. On the other hand, in the solid phase, there are many different ice phases that are known. So what we are familiar with is what we have in our fridges is what is called the ice 1H, which is the ice that is formed at ambient pressure or close to the ambient pressure and ambient temperatures. And so that ice has well-defined geometry of the hydrogen bonds. However, as you vary the pressure and you vary the temperature, so if you go higher in pressure and lower in temperature, many different ice phases emerge that become stable in well-defined regions of the phase diagram. And so these phases are still solid, so they have a crystalline position for the oxygen atoms. Some of these phases also have a crystalline position for the hydrogen atoms, so are ordered. Other instead are still disordered ice phases, so only the oxygen positions are fixed in the crystal, but there is disorder in how the hydrogens are placed. And so in these phases, all water molecules still form 4 hydrogen bonds, but the orientation and the arrangement, the special arrangements of the water molecule changes. As of today, I think we know 20 crystalline different ice phases. And that doesn't mean that there may be other ice phases that are not known yet. And so in this configuration, the hydrogen bonds are different, the strength is different because the geometry, the special arrangements, so the three-dimensional arrangements of the water molecules within the crystals is different. And so the hydrogen bond, as a definition, is the same across the different water phases, but its strength changes depending on the local arrangements. And so the different ice phases have different strength of the hydrogen bonds, liquid water is a different strength, and the gas phase has a different strength.
Mm-hmm. Okay. If we compare the ice phases that you would have, is it possible to move between those in a continuous manner? Let's say you have a threshold temperature given a certain pressure, and as soon as you cross over that, it will transition from one phase to the other, or is there some sort of lag in terms of minimal energy that needs to be added to the system to move from one phase to another in that kind of circumstance?
Okay, so definitely it's possible to move from one phase to another, and there will be a phase transition. It's the same as happens when we freeze water into ice, or when we boil liquid water into vapor. And so there will be a point where there is a coexistence between the two phases, and as you move a little bit on the left or on the right of that coexistence line, then you enter the region of stability of one of the phases. And so for ice, it's definitely possible to go from one phase from another. Obviously, in the solids, these transitions are much lower because they require the rearrangements of the entire number of water molecules in the solid, where everything is very compact and rigid. And so it requires some non-trivial experimental setups.
Mm-hmm. Okay, but nevertheless, as long as the temperature is within the part of the phase diagram where it corresponds to another phase of ice, let's say, there will be a transition given enough time. It's not that there requires a minimum additional threshold energy to sort of kick off this reaction or this change in phase.
No, is due to the equilibrium thermodynamics, and so as you enter the region of stability of one phase, then the water molecules will rearrange slowly in order to reproduce that phase, because that is going to be the minimum in the free energy landscape. It will require, as I mentioned, time, and so there will be the possibility to define and to have like metastable phases that exist only for a limited amount of time while they are transforming into the most stable phase.
Okay, very interesting. If we now focus on the modeling aspects of this, the way we've modeled water in the past, the way we've modeled it in the very recent past as well, and then the findings ultimately that you were presenting in this paper. Would you mind giving some background to how we modeled water in the past? Have we used one universal model to try and cover all phases, or have we used more specialized models for the different phases and then had to patch those together with, let's say, experimental results of the phase transitions?
Of course. So the first simulations that were carried out in the 70s were done using a simple models that try to capture the physics of a water molecule. So you can imagine a water molecule as a triangle where the oxygen is the vertex, and then there are the two hydrogens that are at the end of these OH bonds. So since the oxygen is more electronegative, you will expect that there will be a partial negative charge on the oxygen side. Since the hydrogens are more electropositive, there will be some partial positive charge on the hydrogen atoms. And so this will give somehow the distribution of the charges on the water molecule, and the water molecule was described as a stick and ball representation. So you have a ball describing the oxygen with a negative charge, with a partial negative charge, and two other balls describing the hydrogens with a partially positive charge, and the bond between the oxygen and the hydrogens were taken from experimental measurements. And the charges were parameterized in order to reproduce the dipole moment or something similar to the dipole moment of the water molecule. And then there are the water-water interactions. So if you take another water molecule and you make this second water molecule interacting with the first one, there will be some intermolecular interactions that traditionally, historically, were described by a Lennard-Jones potential that described the dispersion energy at long range and the repulsive wall that you find when two water molecules try to penetrate each other, and this is due to the repulsion between the electron cloud. So the initial water molecules were based on what is called molecular mechanics, which was developed in the 50s by Hill and Westmeyer and Meyer, that tries to describe the molecule really like a mechanical object. So there will be some springs that describe the vibrations of the bonds, and then these electrostatic interactions based on partial charges that try to reproduce the electron cloud distribution around the molecule. And so these are what are called classical force fields, and they've been the workhorse for molecular simulation since the 70s. I think that the first force field that was developed for a general system was put forward in 1968 by Lifson and Warshall, and from there many different variants of this type of representation were used to describe molecular interactions. And so from that point on, many different research groups have developed force fields for water, trying to reproduce a subset of experimental measurements or trying to reproduce some ab initio, data obtained from solving the Schrödinger equation, which is the quantum mechanical solution, so it should be the rigorous solutions of the electronic problem. However, because of the limited flexibility of a force field, because you are really a force field that can only rely on 3 partial charges and a few Lennard-Jones parameters that describe the intermolecular interactions, these force fields were never able to reproduce all the properties of water. And for a long time, there was this adage that in molecular simulation, essentially we have the exact representation of the system that we are interested in, and therefore what we get out of a molecular simulation depends on these approximations. And there was this belief that we will never be able to develop a model capable to describe the properties of any substance across the entire phase diagram. And so this was, so there are like tens and tens of water models that are able to reproduce specific properties, but never be able to be completely transferable. Of course, with the developments of better hardware and better software, and with the introduction, I would say, of the Carparinello method, which was a way to use quantum mechanical solutions of the Schrödinger equation on the fly to propagate molecular dynamic trajectories, several research groups also try to use directly quantum mechanics to solve the problems of water. Within these quantum mechanical approaches, the most common method used is density functional theory, which is the workhorse, I would say, of molecular simulations that are of ab initio type. So they are trying not to rely on any parameterization, but they're trying to solve the Schrödinger equation within a certain theoretical model. However, also density functional theory suffers from some limitations and is also very expensive. And so in parallel, essentially from the late 90s and the early 2000s, there were these two different parallel routes of describing water, using force field that were becoming more and more sophisticated, or using ab initio models, and so density functional theory, and also in that case, density functions were making better and better. However, until 2000, until the last 10 years, I think there was still a lot of uncertainties on how to model water. And that is where I think our contribution came up, because we tried to find a way to combine the efficiency of force field-like simulations with the accuracy of quantum mechanical simulations. And we did that by exploiting or building upon the emergence of machine learning and data-driven approaches that allow us to learn a lot of complex molecular interactions given a reference data that can be of very high accuracy. And so in order to do this, what we developed was this data-driven many-body framework that I'm trying to explain now what is data-driven and what is many-body. So when we have a molecular systems made by n molecules, so by a number of molecules, we can calculate the energy of this system by summing all individual n-body contributions, which means that we are going to calculate all the energies of the individual water molecules, then the energies of all possible two-body contribution, which means is the energies of a dimer minus the energies of the monomers that form that dimer. And then we are going to calculate the energies of the three-body, which is the energies of the trimers minus all the constituting dimers and monomers and so on. And if we sum all these contributions, at the end we get the same total energy that we will get if we could solve the Schrödinger equation for the n-body system at once. So these many body effects I usually try to explain to the public, have a lot to do with how molecules see and interact with each other. And there is an analogy, I think, with how we behave in a society or in a group of people. When we are alone in our rooms, we behave in a certain way because nobody is watching and we are free to do what we like. If someone enters the room, then our behavior changes depending on whether we know that person or not. And so this is like a two-body effect because our one body, so our behavior, has been affected by a second person. If a third person shows up, the dynamics of the first two also changes because of the effect of the third person. And this propagates until we reach a group of people. And so when we have a lot of people in a room, definitely each person is affected by the overall dynamics of the entire group of people, but we are more strongly interacting with our local neighbors. And this is exactly how water molecules behave. Because when we have a glass of water, definitely the macroscopic properties, or what we call like a mean field interaction among all water molecules, depends on the total number of water molecules. And so we can see these fluctuations that are common across the entire glass of water. However, each water molecule is going to feel more strongly the local interactions with the water molecule in the first solution shell or in the second hydration shell. And so that allowed us to use this many-body expansion by dividing, however, the contribution from in local contributions and mean field-like contributions. The local contributions are the interaction that depends on a few water molecules at a time. And those are really quantum mechanical because the electron clouds overlap and they give rise to quantum mechanical effects like Pauli repulsion or charge transfer. The electrons are shared. In those cases, we need quantum mechanics. But to describe instead the interactions of a water molecule with another water molecule that is very far, we really don't need the quantum mechanics of the dimer, but we need the quantum mechanics of the monomers that is modulated by the behavior, by the collective behavior of the entire system. So this is like a mean field-like approximation. And so by doing that, we have been able to calculate at a high level the low order terms of the many-body interactions. And so we use what is called couple cluster, which is the best quantum mechanical theory that we can apply given the current computational resources. And then we glue these quantum mechanical representations with a mean field-like representation based on a classical electromagnetism, so essentially solving Maxwell equations of electromagnetism. So the quantum mechanical part, instead of being solved on the fly when we do the simulation, we calculated large data sets and we use machine learning to feed these two-body, three-body, and more recently also four-body interactions into what are called permutation invariant polynomials, that are mathematical functions that satisfy the invariance of the symmetry of the Hamiltonian, so of the energy of the system. This permutation invariant polynomial essentially guarantee that if we permute two equivalent atoms, so two molecules, identical molecules, the energy of the system doesn't change. And also guarantees that if we rotate the system, the energy of the system doesn't change, and if we translate the system, the energy of the system doesn't translate, which are the properties of the Hamiltonian, which is the energy operator that describes the energy of the system. And so by gluing all these components together, so these data-driven many-body terms with a higher order and long-range interactions, we have been able to develop a model that is highly accurate because it's based on the best quantum mechanical methods available, and is still effective because provides energies and forces for any configuration of waters from gas phase to liquid to solid in an efficient way. And so we have been able to simulate water across the entire phase diagram.
One follow-up question on this, these different kinds of interactions that you have to the other molecules that are close to the one you're considering and the ones far away. Naturally, part of this, as you also explained, is you have some form of power law, I would assume, decay. So let's say your molecule is here, the ones that are close, they would interact very strongly, and this would decay probably exponentially, I would assume, with molecules as they divert. The less evident part of this is, as you said before, the ones that are close, you would need to take quantum mechanics into account and model those with the help of the Hamiltonian, and then you would have a mean field approximation for the ones that are far away. Is there some way to bridge these two qualitatively different approaches to modeling interactions for something in the middle here? So the edge cases are clear, like you get some contribution from this, and here you can use mean field theory. Here you need to use quantum mechanics and be very accurate, but for the ones that are close to the middle, is there some way to overlap these two, or how do you approach the middle ground?
Yeah, so this is a great question because, of course, the mean field approximation becomes less and less accurate as we go to smaller and smaller systems. While instead the quantum mechanical representation becomes more and more expensive and probably not necessary as the number of molecules increases. And so there will be a middle ground where these two things merges together. And so in our approach, what we have is that in the data-driven representation of the low-order terms of the interactions, we use a switching function that smoothly decays to zero, so switch off these quantum mechanical interactions as the molecule becomes, when the separation between the molecules becomes larger and larger. And we find this region where the transition occurs by looking at how well the mean field approximation is able to reproduce the quantum mechanical energies as a function of the distance. And we find the region where the classical mean field approximation is already gives already a good accuracy compared to the quantum mechanical representation. So in that region, we have a switching function that smoothly switches to zero the quantum mechanical contributions.
Okay, so you could think of it as if you have that your entire interaction is the sum of a quantum mechanical interaction for that given molecule that you're considering, assuming you're considering one molecule at a time, which is not evident, but let's use that as an analogy for the moment. And then you have another part of that sum, which is the classical effect. And you can just more or less average those or do a weighted average between them and still get an approximation that holds up in a reasonable way? Or am I thinking about that wrong?
It's somewhat different. So let's imagine that we have two water molecules. And so in these two water molecules, we are calculating the energy as a function of the distance. And so in our model, we have a mean field representation of these interactions that is on at all possible distances. As the distance becomes closer and closer, however, there is a data-driven many-body term, a two-body term, that kicks in because as a function of the distance, at some point the electrons cloud overlap, and the classical representation is not good enough anymore because the electrons are fermionic particles, and we need to take into account Pauli principle that doesn't have a classical analog. We also need to take into account charge transfer that doesn't have a classical analog. And so in this region, we have the data-driven two-body contribution that kicks in and corrects essentially for the deficiency of the classical model. And there is a region where the data-driven many-body term smoothly grow until it reaches the full contribution. And so in the short range, we have a sum of both the mean field representation and the data-driven representation. And the sum of these two contributions is going to match exactly what the higher level couple cluster energies give us. And so essentially we have a short range, the sum of these two contributions, and then as the separation increases, the many-body term goes to zero, and in the long range we only have the mean field approximation.
Okay, that makes perfect sense. The follow-up question I would have to that is, in the case of two molecules, this is clear. You would have one long-range interaction that goes to zero, and then one data-driven one that becomes more prominent as they were very close. What happens if you have, let's say, three of them? I would guess. So in the case of two, it's quite clear, right? Because you have two of them, you could sort of neglect the geometry of the situation, or at least to an extent. I guess since they have dipole moments as well, then you can't quite neglect it, but to a large extent, I guess you could. If you have multiple, like more than two molecules in the system, also the individual constellations between the other molecules has to play a role, I suppose. How do you take that into account in the data-driven approach without making it exponentially diverge in terms of complexity?
Yeah, so that becomes like an software engineering problem. So also when we have a trimer, so we have three water molecules, again we have a two-body term and now a three-body term. So the two-body term is exactly as in the dimer, as we can calculate, we look at all possible dimers, and when the distances of these two dimers become smaller or longer, we have the representation in terms of the sum of many of the data-driven contribution and mean field, or just the mean field contribution. And then we have a three-body term that depends now on the distances between all three water molecules. And so in our case, we use the oxygen-oxygen distance as our key distance to determine the special cutoff. And so our three-body term has a switching function that depends on all three monomers. And so it switches to zero as one of the monomers go farther and farther from the first two, from the dimers. And so our three-body contribution becomes smaller and smaller, and the many-body term goes to zero as one of the monomers leaves essentially the trimers. And so in our switching function, we have a product of three, we have the sum of three terms, and each term is the product of two distances, which is the distance of molecule 1 to molecule 2 and molecule 2 to molecule 3, or to molecule 2 to molecule 3, and so on. And so essentially we have a permutation of distances in our trimers, in our switching function for the trimers, and this permutation essentially guarantees that any time that one of the three water molecules leaves the trimer or goes beyond a certain cutoff, the many-body contribution to the energy goes to zero, and only the mean field representation survives.
Yes.
Obviously, So to go back to your question, obviously, this becomes unaffordable if I need to calculate all possible n-body contributions, in the sense that if I need to have a data-driven representation also of the 5-body, 6-body, 7-body, because then the complexity becomes very large. But the many-body expansion is actually, for the energy, converges very quickly for systems that have a large energy gap between the valence and conduction band. So for all the insulator, like water, the wave function, the density are very localized, which means that quantum mechanics only plays a role very locally. Is what Walter Kohn, the Nobel laureate for density functional theory, called the nearsightedness of electronic matter. Because for systems that have this big gap, quantum mechanics is very local. So you don't need, for systems like water, we are not going to need ever to describe explicitly 5-body, 6-body, 7-body interaction. So as long as the number of bodies that we need to deal with is small, then the complexity is still manageable.
Okay, I understand. And the cutoff function is clear from the way you described it. You can parameterize that in the case of 3 molecules, let's say, with the individual distances between them. I wasn't so much referring to the cutoff function, though. So the cutoff function, I think, is clear now, given what we just said, like how you could parameterize that. I'm thinking more in terms of the complexity. Let's take the 3-molecule case as an example. You have 2 parts to this. You first of all have the cutoff that tells you how much to attenuate this contribution, but then you have the contribution itself. And you have many different options, presumably, in how you would parameterize that contribution. For example, you could have a contribution that depends only on the distance between, let's say, the center point of these atoms, and say that's the only parameterization I have of this. You could also have something that takes into account the dipoles of these individual molecules to determine another size of the contribution. How sophisticated is the parameterization of this 3-body contribution? Is that something you take into account and have to take into account, or can you be like also due to the localization of the wave function quite sloppy, let's say, or not as granular in how you parameterize that function?
Yeah, no, actually, so the parameterization must be very sophisticated. And so in our explicit 3-body contribution, we have this permutation invariant polynomials that are a function of the coordinates of all atoms that makes the system. And so for a 3-body, we have 9 atoms. And so we are going to have a polynomial that depends on the coordinates of all these 9 atoms. And so if you think in Cartesian coordinate, each atom has 3 Cartesian coordinates, x, y, and z. And so our polynomial is going to be a function in principle of 9 times 3, 27 coordinates. We remove the center of mass, we remove the rotations, and so there are going to be 21 coordinates that are going to be part of the polynomials, which is necessary in order to describe exactly what you mentioned. The special arrangements of these 3 water molecules in the liquid can be completely very different. I mean, it's not restricted to certain configurations. So our polynomials needs to be able to describe all possible configurations, all possible 3-dimensional arrangements of these water molecules. And that is what makes our model very transferable, because it's able to reproduce all possible 2-body configurations or 3-body configurations that we are going to see not just in the liquid, but also in the solid phases or in the gas. And because of this flexibility in describing energies for these systems, that doesn't depend on the thermodynamic state point, but is completely agnostic of what kind of system we have or what kind of phase we have, the model then is able to seamlessly reproduce all the energetics of water independently of whether it's a solid, is a cluster, is a liquid, is a supercooled liquid, and so on.
Okay, I understand. If you would apply this model now, given the fact that you parameterize these with 27 variables, let's say in the case of a 3-molecule interaction, if you want to somehow simulate not just the phase diagram of water, which we can have a look at in the paper in a second, but also, let's say, for, I don't know, industry applications, you would actually want to simulate what happens to this lump of matter, let's say. is this model in any way applicable to that? And if it is, how would you go about actually parameterizing those functions as you wish to simulate something?
Yes, so that is actually so. This project started as an academic question at the beginning, and the question was like, is it possible to develop a molecular model on a computer that is able to reproduce the properties of a substance across the entire phase diagram? Because as I mentioned, until 10 years ago, there was this idea and belief that a computer model would never be able to reproduce the thermodynamic, structural, thermodynamic, dynamical property of a substance across the entire phase diagram. So then when we developed our model, this ambipole water model, and we started calculating all possible properties, and we were seeing that the model systematically and consistently was able to reproduce and predict the experimental values quite accurately, we thought that the academic question was answered. And so there was a second question, and the second question was like, so what? Can we use this model to do something that goes beyond the academic world or the fundamental physical sciences and can actually be used to guide processes or developments of industrial processes or something that can be used for technological applications? And we are currently doing this, or we started doing that, by looking at how, for example, materials can be optimized to harvest water from the atmosphere. In this way is essentially having a material that acts as sponges that can provide water in regions where water scarcity is a problem, or in arid regions that are not close to any water source. And so these porous materials have been shown that can act as a sponge during night in arid region. They can absorb water, and then during the day, because of the change in temperature, they essentially let water evaporate. And if you put a system in if you put the material into a closed system, then the vapor water is going to condense on the wall of the box that you have, and then you can collect that water as a drinkable water. And since our simulations, our water model is able to reproduce the properties of water across the entire phase diagram, so the vapor and the liquid equally well, we are studying how the mechanism of absorption into this material, and we have just started a project that has the goal of optimizing these materials for water harvesting, but also for water desalination, for example, or for mining precious metals from aqueous system, like lithium ions are going to be in a great demand in the near future because of the batteries. And so if we can recycle lithium ions from aqueous solution and recover these lithium ions, that would be a great advantage. And so we are trying to connect now fundamental physical sciences and computational molecular sciences to real-world applications. And I think it is possible by combining different expertise between theoretical and computational chemists as us, synthetic chemists, and then engineers a little bit later.
Okay, very interesting. Let's have a look at the phase diagrams that you've actually generated with this. And I think in combination with that, I think this one is the best one to have a look at. In combination with that, we can talk about how you would parameterize this either in an application or just for the experiments that you had. So we have now a number of different phase diagrams here generated from different kinds of algorithms. I would like you to give just a quick introduction to like what this figure represents. And once we've done that, maybe we can focus on how you actually generate a figure like this, given what we've just described, given the parameterizations and so forth.
Yes, so we usually think in a computer simulation that the phase diagram is the holy grail in the simulation of the substance, because if a model is able to reproduce all possible phases correctly, it means that the model has the right physics, and so it's going to make predictions also for properties that maybe have not been determined yet experimentally. And so in each of these panels, there are 6 different phase diagrams calculated using different water models. The red lines are the a coexistence line of the experimental phase diagram, which means that these lines, along these lines, there is the coexistence of two phases. So just looking, and instead in the models, maybe if you go to the previous figure, just to show with the experimental phase diagram is the top, this one. Okay, so yes, if you look at the experiments, so each of these shaded colored areas is a region of stability of a particular phase. So liquid water is in the blue, and so as a function of temperature, which is on the x-axis, and the pressure on the y-axis, you see that water can exist as a liquid in this region blue. And then if you go from a pressure of 1 atmosphere, so close to the x-axis, and then you increase the pressure, you see that there is a line that divides the blue region from the green region. So that line is the coexistence between ice 1H, which is the common ice phase that we see when we go skiing or when in our fridges, and liquid water. And so along this line, both phases coexist. You have an equilibrium between the two phases, and both of them exist in the same proportion. However, if we go a little bit on the left or on the right of that line, everything transforms into ice if you go to the left, and into liquid water if you go to the right. Essentially, this means that if you go to the left, all water is going to freeze into ice, and if you go to the right, all water goes, all ice transform into liquid water. And then if you keep lowering the temperature and increasing the pressure, you reach a point where there is now the intersection of different lines. So there is a triple point there. So the triple point means that now three phases are coexisting, and there is liquid water, ice 1H, and then this ice 3. And so the ice 3 is a different phase of ice, has a different arrangements of the water molecules, and exists in this small region of relatively high pressure and lower temperature. And now again, if you go to the left of this ice 3, you are going to cross another line, which is the coexistence between ice 2 and ice 3, and again, along this line, both ice phases are present, but if you go on the left, ice 3 will transform into ice 2, and if you go to the right, ice 2 will transform in ice 3. And then you can keep doing this for all other phases. So if you increase the pressure, you will transform ice 2 into ice 5, or ice 3 to ice 5, depending on the temperature. And then once you get to ice 5, if you keep increasing the pressure, you go to ice 6. And so this, the low pressure region of the phase diagram. If you keep increasing the pressure, you are going to see different ice phases. And if you increase the pressure a lot, the water molecule will dissociate. And then you have what are called the superionic phases of water, where protons are free to move around. We were interested in the low in the low pressure region. So now we can go to the comparison of the different models. And so now the red lines represent the experimental phase diagram, and the other, all the other panels show a comparison with existing water models. As I mentioned at the beginning, force fields are where the workhorse for computer simulation. They are still the workhorse because they allow and they enable simulations of extremely large systems. But you can see that the predictive power of these models, like T4P 2005 and T4P ICE, is somewhat limited. You can see that some of the ice phases do not appear in the right temperature and pressure region. Some of them exhibit a much larger stability region, like the ice 3, which is this brown shade in T4P 2005 and T4P ICE, is extremely larger compared to the small region that exists in the experiment. Then on the right panel of the top row, there is another force field, which is I-amoeba, which is a little bit more sophisticated because it includes also polarization. It's still parameterized to reproduce some experimental quantities, but it's a little bit more physical in the sense that it includes the polarization between water molecules. And you can see that maybe has some improvements because now ICE5 shows up as a larger phase, but is still limited in the ability to describe the other phases. Mm-hmm. In the bottom row on the left, there is a neural network potential. So now with the development of artificial intelligence and neural network and machine learning, what researchers are doing are to use this neural network to fit density functional theory potentials. So this scan is a density functional that were used in ab initio molecular dynamics simulation that, however, are very expensive. And so what now we can do is to use those ab initio simulations that are relatively short to train a neural network that is going to represent that density functional model, but at a faster, but is much more efficient and faster. And so this DNN scan is a neural network potential trained on the scan functional. And again, you can see that is getting a little bit better compared to the force field, because now you see also the ICE2 phase that instead was not present in the other classical in the force field, but the regions of stability of the different phases is somewhat misplaced. The middle panel, RepB0D3, is another density functional, and in this case, the researchers have used ab initio simulation, so they didn't use any neural network potential, they used the RepB0D3 to calculate the phase diagram. It's a little bit more complicated than that. They use a neural network at the beginning, and then they transform the neural network into the density functional. And so this is closer to what ab initio simulation would predict. Mm-hmm. And on the right is our MB-pole, the phase diagram of MB-pole. As you can see, it's very close to the experiments. Clearly is a quantum leap, I would say, compared to what was done in the past. I mean, compared to the force fields and compared to density functional theories, definitely is a clear improvement. I mean, we can almost say that MB-pole is, you can almost drink MB-pole. It's so close to water that it shows the same properties, the same behavior of real water. There are obviously some inaccuracy, and it is good that there are inaccuracy because it's still a model. We are not, our model, our MB-pole is not real water, and so there must be some differences, but these differences are very, very small. So you were asking how we calculate this phase diagram, and calculating the phase diagram is a tour de force, because essentially we need to calculate the equilibrium between different phases. So we need to calculate what are called the free energy differences between different phases, and we need to find the pressure and temperature where these free energy differences are equal to zero. Because when they are equal to zero, essentially we are on the coexistence line. Both phases exist. And so along this coexistence line, essentially each of these points on the coexistence line is like the melting point of one of the ice phases compared to liquid water. So if I go to the green, to the coexistence line between the green and the blue areas, each point there describes essentially the melting of ice 1H into water as a function of pressure and temperature. So the first step of calculating the phase diagram is to calculate the melting point of all these ice phases relative to water. And so this means that, of course, there are some of these ice phases are in contact with liquid water, and so we can calculate the melting points of each of these ice phases as a function of pressure and temperature. Then what we do, we connect all these points to calculate the coexistence lines, and you will see that some of these coexistence lines will intersect, will cross each other, and so in this way we can determine the triple points. And so then by connecting all these dots, we have the phase diagram. In our case, we also did one step forward. We calculated the fully quantum mechanical phase diagram of water, which means that we also took into account the fact that even water molecules behave quantum mechanical. So we need to describe the wave function of a water molecule, not just the wave function for the electrons. And so we perform additional simulation to calculate what is the free energy difference between the classical representation of water and the quantum mechanical representation of water. And so what is shown here is the quantum representation of the phase diagram of water using our model. If we go to the previous figure, I can show you what is the difference. No, the top one.
Okay.
Again, a little
This
bit
one?
up. Yeah, yes. And so here is what essentially how we calculate the phase diagram. We built a neural network trained on MB-Pol, and this is the top left panel. We did that because the neural network is much faster than our MB-Pol model. But you can see that the neural network doesn't reproduce exactly the entire phase diagram. Then we did what is called free energy perturbation, which is a way to morph one model into another model when the two models are very close to each other. And so we use this free energy perturbation to calculate what are the free energy differences between the neural network and the actual MB-Pol potential. And we got the top right phase diagram. This is a classical phase diagram in the sense that we are neglecting nuclear quantum effects. So hydrogen, for example, is very light, which means that the thermal, the Broglie wavelength, which is a measure of the quantumness of a particle, is relatively large, which implies that we should take into account nuclear quantum effects when we describe the motion of the hydrogen atoms. And that is what we did, going from the top right panel to the bottom left panel. We calculated what is the free energy difference between the classical representation of water and the quantum representation of water. And you can see that the phase diagram improves, which is fundamentally very important, because the neural network is an approximation of MB-Pol. And so we expect the neural network to be not exactly MB-Pol. And so when we morph into MB-Pol, we get an improvement. Then we know that nature is quantum mechanical, and so we expect that if we include these nuclear quantum effects, the agreement with the experiment should improve. And in fact, that is what happens when we go from classical MB-Pol to quantum MB-Pol. And so that is how we calculate the phase diagram. It's really a tour de force, because there are many different calculations that are very sensitive to the amount of sampling, and so the simulation must be long enough to guarantee that we are in equilibrium to calculate all these coexistence lines.
Okay, that's a great explanation. Thanks for that. We are very short on time now, so we need to start wrapping up. Before we do, I would just like to ask, in addition to the points you raised before, whether there are any additional takeaways from the research you've done that you feel would be interesting to progress going, or to investigate going forward. So are there any other avenues, like anything else you would like to investigate after you've seen these results now? If you could shed some light on that.
Yes, so we believe, obviously we are a little bit biased because it's what we do, but we believe that this data-driven many-body framework provides a coherent and comprehensive theoretical and computational framework to model any molecular system that obeys this nearsightedness of electronic matter, so systems where the many-body expansion converges quickly. That opens up the possibility to study all possible molecular fluids of aqueous solutions. I mentioned water desalination. How to separate ions from water is something that our model will be able to do well, and so they can provide molecular level insights on the type of strength of interactions, so driving forces that led molecules and ions interact differently depending on the substance or the substrate of the material they are interacting with. We also believe that this can be very useful to understand the hydration phenomena of biomolecules, for example. And we also believe that our framework can be extended to large molecules, because this many-body expansion can also be applied to covalently bound molecules. So at the moment, we look at a bunch of water molecules. The water molecule is relatively small, it's just 3 atoms. But we think that we can describe very large molecules where we can isolate what we call naturally building blocks that are going to act as our monomers in this many-body expansion. So if you imagine a protein, for example, we can describe each amino acids in terms of functional groups, like the peptide bond or the side chains and things like that. And each of these building blocks can be represented within a many-body framework, which means that we think that in the future we will be able to use like these building blocks, like a Lego blocks, to connect them to each other, to make any large molecules that we want with an accuracy that is the accuracy of couple cluster, which is what is usually called the gold standard for chemical accuracy, which implies that our simulation should be predictive and accurate, which means that we will be on par with experiments, and there will be a strong synergies between experiments and simulation because now they are speaking the same language essentially. And so in the future, just to conclude, what we would like to do is to use these simulations as a way to generate data that then can be used in generative AI to build materials or molecules that maybe do not exist yet in nature, but they can be tested on silicon and a computer, can be optimized, and that can open up many different applications, from the design of biomaterials to drug discovery and things like that.
Mm-hmm. Okay, great. I think as far as the interview goes, we're over time now, so I'm going to cut it here. I really appreciate the discussion. Thanks a lot, Francesco, for joining, and yeah, thanks.
Thank you for having me here, and it was very nice to talk to you and share our research.